Hi, so we are now with the second part of the first week. And really what I want to discuss now at the beginning is how we are going to approach studying these new materials, new processes. And basically the first thing we have to do is to acknowledge that they are different. This have many implications, especially we'll have to check all the time if what we believe to be obviously true or always happen still holds. It's molecular electronics, plastic electronics, but they are semiconductors too. And what we'll do is we'll start by understanding how they behave as semiconductors. And out here we'll leave the why for later because getting into the physics of the carrier motion in disordered molecular semiconductor is a big challenge. And this is not the purpose of this course. But we'll touch a little bit on it. And what I brought is some animation that will illustrate the things that we are not going to touch. And of course, once we simplify the picture and ignore many details, it means that we make some assumptions. And we'll talk about these assumptions as we go along. So we have a polymer film, and this is a sketch where you see chains. This could be polymers. And they are spread. Sometimes you can think of them like a spaghetti. Sometimes they are more ordered. There could be regions where it looks like it's a crystalline, so it's polycrystalline regions which are crystalline, and regions which are not. And really the question is what's going on here in terms of the electronics. So basically these are not quantum wires all the way. And if we look at them, there are parts of the polymers which are coherent segments or conjugated segments, and they form like states, or a quantum wire or a quantum well. And really we can take the polymer, sorry, and divide it into the states. Of course, we don't do the division, it happens by itself. And the coherence length varies in space and along the polymer. It will be different for different polymers. And it has a lot to do with the morphology of the polymer itself. And really these are the states that the electrons know about, and when the electrons will move, they'll move from one state to the other. And basically the only thing that the polymer is doing in this picture is creating the morphology. And of course only is understatement because morphology is the name of the game many times. And now we need to send an electron from left to right, and it really needs to choose how to make it through space. And of course the morphology will dictate the path it will take and how easy it's going to be. So let's let the poor soul start moving. And what it will have to do is to jump from one place to the other. So you can see it jumping, and every now and then it's a bit difficult to continue. It stays and it doesn't move. And the question is why that might happen. Part of the answer could be here. If it needs to jump a long distance, it's more difficult, so it takes time to make the jump. The other thing that happens is that we are not showing here another dimension of the problem, because here we have the x and y, but there are also the energy of each of these states. So if we do the same thing as before, and we add the energy of different states, so now the charge will hop in space and in energy. And you can see here on the right the energy. And when it happens to be in a low energy site, it's like being trapped. It takes it a long time to accumulate energy and be released. And of course, understanding the transport in something which has a three-dimensional in space, because let's face it, the materials we make are three-dimensional. The energy adds a fourth dimension, and then the motion, if you like, time is like the fifth dimension, not the fifth element. And analyzing it all in an ab initio way is not trivial and not practical either. So what are we going to do in this course? Actually, we first of all set the goal. Our goal is to understand devices that are made of organic materials. The goal is not really to know everything there is to know about organic semiconductors. All we want to know is how the devices are working, and that really defines a small set of properties we are going to be interested in. There is a lot more that's happening, and we are hoping that all the processes that we neglect are not really important, and we really know what's going on. And using what we decide to be important, we can progress. Of course, this was never done in one shot. There was a lot of trial and error. So now that the field is approaching, depending how you count the birth date, something like 30 plus minus 10, then we can relatively safely use what we are going to study in this course. So what we are going to start with is a very broad approach, a bird's view. We'll consider them as wide bandgap semiconductors because if you think of the LEDs, if they emit in the blue, it's a 3 electron volt bandgap. These materials are almost always unintentionally doped. Doping has started to develop in this field, but it's still not as developed as in inorganic semiconductors, and it's still the most important part of the device is typically the undoped one. And the last thing is the mobility is low, because we saw the charges have to jump from one place to the other. Sometimes it's a long jump, sometimes it has to jump up in energy. So it takes time, and it's the whole thing is slow, and mobility is low. So basically what we are going to look at is transport in insulators, because insulators are wide bandgap, and the really good books that have been written on transport in insulators are a good starting point for transport in organic materials. So semiconductors, insulators, etc. So we'll remind ourselves a little bit about band gaps and types of materials. So I brought here the fourth categories that are most common. So on the left we have the intrinsic material, we have the conduction band, the valence band, and the Fermi level is positioned right in the middle. When the material is doped and it has more electrons than in the intrinsic state, so if it's the n-doped, the Fermi level goes up and approaches the conduction band, and the position of the Fermi level is linked to the charge density. The same will happen with hole doping or p-type doping. The Fermi level will approach the valence band. And in cases where the Fermi level is up into the band, we call it metallic, and that's really the way metals work. We have a lot of charges that can conduct, and that's what's behind the high conductivity. And why do we say that the intrinsic materials might be insulators? because if it is a wide band gap, there are no thermal carriers here. So basically there is nothing that would naturally conduct. And why we still call it a semiconductor, although in some books it is insulator, because it doesn't have its own charges, but if we'll find a way to inject them either through light or by applying a voltage, then if you place a charge here, it will know how to move. But as long as there are no charges here, of course, it's an insulator. So these are the basic ground rules or the layout of the problem. But since we are going to stay in the device physics, semiconductor device physics level, I thought it'd be a good idea to remind ourselves a few of the basic points in this field. So let's start with two of the basics, the density of states as a function of energy, and the Fermi-Dirac statistics, or the probability of a state at a given energy to be occupied. And we know that if we integrate across this term, we can derive the total charge density that is occupying the band. And often we forget that we really need to know the density of states. And of course, the statistics is important, but we take it as a given, and it's the Fermi-Dirac statistics. So just a reminder, when we are talking at inorganic semiconductors or other semiconductors that have parabolic bands, this is the shape of the bands. This is the band edge. In this case, it's the conduction band. And the shape is linked to the effective mass of the particle. In this case, is the electron. And this is its shape. The other thing we need to remember is the Fermi-Dirac statistics. And this is the term that we use to describe it. It's not just we use this is the term to be used. And this is its shape. Below the Fermi level, everything is fully occupied, and far above it, it's all empty, and there is the transition period, and the width of this transition region depends on the temperature. And really, the Fermi level has many meanings. Some of them are really deep. But in our context, it is the value that will make this equation be correct. Here we can visualize how the position of the Fermi level relative to the band affects the charge density in the band itself. On the left, we see the case where this is the Fermi statistics, and the Fermi level is within the band gap. It is below the conduction band. What we see here is the exponential tail that penetrates the conduction band. And if we multiply the two and enlarge it a little bit, we see that there is some occupation within the band, and it drops here exponentially. If we take the Fermi level and we shift it to the right or high, and in the extreme case we cross the conduction band, we see that some of the states here are completely full. The semiconductor is said to be degenerate, and this is really the high density case. And we see that really the important parameters is the energy difference between the Fermi level and the conduction band. And what I didn't mention before is that really we were so happy to use the Boltzmann approximation, and of course, or not of course, you should know it holds only in this case. So that's why many times we are interested in the not too high density case. So we can set this one aside and forget it for the time being. And why we are interested in the low density case? It's not because we can't really solve this equation. It's just an integral. We can always solve it. The question is, do we really want to solve it? And luckily, as I said, if we are in the low density regime, we can approximate this integral with the Boltzmann statistics, which has a really nice form. All we need to know is this term and where the conduction band is. And if the semiconductor has parabolic bands, we know how to derive this value. But what's more important is that we have this term here, which is called the effective density of states at the band edge. And the actual real number to be placed here is important, but not so much for our discussion. But we need to remember that it's important to know it for this approximation to be useful at all. So we've seen the parabolic bands, and as you saw with the first slides and the animation, a charge that is hopping between states, it's really hard to believe that the states it is hopping through are really arranged to match this kind of shape. So we need to consider the possibility that there will be other shapes for the density of states. And this is one of the things that distinguish organic semiconductors from many of the inorganic ones, is that we have to consider a different density of states function. And we'll have to ask ourselves, when we have a different density of states, do we know where is the band edge? Can we apply all the things we took for granted when we were dealing with the parabolic bands? And really, we'll have to deal with the question, what do we do if we can't really identify the edge of the density of states? And in some cases, if we fail, it could be really interesting, as you can see here. So one of the density of states that is commonly used is the Gaussian density of states. There are several reasons behind using this kind of density of states. One of them is what we would expect for large numbers. The other is that a Gaussian is something we can easily manipulate and derive expressions based off it. So there's a lot of practicalities behind it, but there's also some physics behind the choice of a Gaussian. And this is, of course, the known shape of the Gaussian, and this is the total density of states that one can occupy within this Gaussian shape. And of course, the Fermi-Dirac doesn't change when we are moving to organics. The physics is still physics. The thermodynamics still hold. Although it would be surprised, some people at some stage thought it might not be the case. But that's beside the point. And again, just as before, it doesn't matter that we are using our different shape for the density of states. The Fermi level still has, in this course, the same practical meaning, that we need this expression to work. And again, if we are doing the same thing as before, we plot the density of states, we plot the Fermi-Dirac statistics. In this case, we start with the high density case, where the Fermi level is really touching the Gaussian, and we see that there is filling of the states here. And if we are at the low density regime where the Fermi level is really down below here, it's around 0.4 eV below the center of the Gaussian, then we really need to blow up the charge density, which is really residing here. It's really at the edge of or at the bottom of the Gaussian. And again, this is going to be the low density regime. And as before, the nice thing about working with the low density regime is that we can use the Boltzmann approximation or the Boltzmann formula. And you can see that once we are in the Boltzmann approximation, the shape of the density of states doesn't matter anymore. All we need to know is the effective density of states. And that's a question by itself, but once we know it, we don't really care about the shape of the density of states. And this is the other property that makes the Boltzmann approximation extremely powerful. So as long as you are in the low density regime, you are really safe. You can use lots of tools that no one thought of organics when they were using them, because we don't really care about the density of state shape. But if you go into a regime where the density starts to be considered high, or into the degenerate regime, then the shape of the density of states becomes really important. And the question there would be, is it really a Gaussian? Are we sure that the tails are Gaussians? And this is really where most of the things are still unknown, although we've made lots of progress recently. So we've discussed the Fermi level and the bands, and it was behind the scene that we were thinking that we know about the bands and where the band edge. We'd like to think of this kind of a picture where things are well defined. We know where the Fermi level is, we know where the band edge is. But now we have to deal with a Gaussian density of states, and it's not so clear where this edge has to be. And we do know that if we move the Fermi level, then the charge density will go up. That's still for sure, and we can do that. I'll move the Fermi level and we'll count the density of charges, and we can see that the Fermi level goes into the Gaussian. It fills the Gaussian completely until it is, when it passes the full Gaussian, you see that it's completely full. This axis is the normalized density, or the total density that can be inserted into this Gaussian. And really, when we look at it, it's difficult to find or decide where the edge is. And more importantly, where we should place the effective band edge, because there is really no edge into a Gaussian. So basically, we have this Gaussian density of states, and we would like to think that we have two levels, or the LUMO and the HOMO, which are the conduction and valence bands. And often in the literature, what you see that people just take this Gaussian and plug it directly on these levels, and they show you this kind of picture. And it's really what they do is they tell you that the band edge is really at the center of the Gaussian. So really, if you like, one of the ways to define the band edge is really the center of the Gaussian. But why choose this one? You can do something different. You can try and estimate what the edge is. So we draw a line parallel to this rise, and we find a second band edge. If we like, we can do even better. We can try and see where this thing starts. So if you like, this is the third option. And of course, if we have a Gaussian, then we can look at the full width half maximum, and that would define another one. So we have like 4 different options. And the question is which one to choose, or if any of them is really what we should be interested in. And when I say we should be interested in, you should remember that this course is a semiconductor device physics course. So when I say we should be interested in, I'm saying that we are going to look for the band edge in the context of this course. It doesn't mean that if someone else decides to define the band edge differently because he's working on something extremely different or in a very different context, it's not correct. Unfortunately, if too many people decide that it's correct, it's hard to argue. But you'll have to excuse me for being the lecturer that in this course, whatever fits semiconductor devices, that's going to be the truth until the end of the semester. So really, this is the end of this lecture, and see you next time.
בכביש, אתה נוסע